thank you very much for the introduction, and thanks, of course, to the organizers for putting this program together. So Khaled asked me explicitly not to mention AutoCube equipment, but I still do it. So it was my privilege already during my postdoc to work on the first prototype motors. Let's just say the operation was a tick more challenging than what you can buy now. But that was okay at the time, no distraction, no smartphone, no WhatsApp, so we had more time to focus, count steps, and make sure the axis doesn't fall off once we did our 5 millimeters in a couple of nanometer steps. So it's of course an essential tool for anybody doing optics on very small objects. So now with the new group in Darmstadt, we are again able to use this kind of equipment to work on optics with 2D quantum materials, which is more or less the name of the session. So I'm doing the introduction to some of the concepts that the other speakers are surely elaborating on. So I'm still amazed how rich the physics is that we can do, starting off from these beautiful crystals like MoSe2, which is a semiconductor with a gap in the visible region. And we can then, in monolayers or in vertical heterostructures, look at the optical properties. In particular, we're interested, well, it's not even a choice. We are working on excitons, because once you excite an electron from the valence to the conduction band, the hole behind binds into this very interesting complex with hundreds of MeV binding energy, and we can then enjoy these different configurations, and we're going to go through different types of exciton engineering in this talk. So one of the advantages of these atomically thin layers is that you can stack them in vertical heterostructures. There's a lot of beautiful work that is, some of it still in its infancy, as you have seen today already, magnificent results on all this. I would like to focus on slightly more niche options for the moment, which I would like to then combine later in heterostructures, but some other bricks, if you want, for building these. So we are looking here at lateral heterostructures, where you have two materials that are covalently bonded in the plane. So it's a heterostructure, but it remains a monolayer. That's one topic. And if time allows, we will go to these monolayers where you have different top and bottom chalcogen atoms, which leads to these dipolar excitons in the monolayer form. So did I skip over the most important slide? Yes, I did. This is, of course, I'm just a spokesperson of a very large consortium. So we have the pleasure to work with sample growth here with Andrei Torchanin's group in Jena. We use HBN flakes to encapsulate these structures from Japan. Theory, partially done with Ermin Malic and Roberto Rosati. They're all here in the audience from Darmstadt. We came by car because of the spontaneous train collapse. And we have big thanks to my colleagues in Toulouse, of course, because while we were building setups and measuring spatial resolutions, a lot of the data I'm going to show you here has continued to be worked on by my colleagues over there. So why are we interested in these new bricks for atomically thin physics, if you want? We want to look at these atomically thin junctions. Yeah, so that's the thinnest BN junction you can have in nature. You can then look at how you can transport optical excitation from one side to the other. When we started the study, it wasn't clear if this bond that in my PowerPoint drawing looks very solid is good enough to support transport of excitons. Then also for the materials in questions, you have very different species from excitons on the left or on the right side. If this is MoSe2 and WSe2, so you have to think about how you convert spin bright into spin dark excitons or vice versa. And also we wanted to look at some new exciton species, which will occur here at the interface. And I'm just gonna give you an update on this. This is more or less also the future plans list, because we did make progress, but also, of course, discovered a lot of additional questions on the way. So how did this start for us working on chemical vapor deposition ground samples? Initially, when we looked at these samples, their optical spectra, even at low temperature, were super broad. And that was surprising because in atomic resolution electron microscopy, people counted defects and they were as good as exfoliated flakes. So the idea was then we take it off the gross substrate, put it into HBN, which I know is a general approach, but that's what we applied here. And this is the first shot we ever had. We immediately narrowed the line widths to something we can now work with, and which is similar now to our exfoliated flakes. As I said, this now goes down to the same values as here, as seen also by many other groups. And of course, for us, it's very important because these CVD-grown samples, these, for instance, lateral heterostructures, there is no other way of obtaining it. You cannot, by stacking, have similar configurations. So we do need to make sure we can access the best optical quality that these samples can provide. So these samples have been around for a while. Yes, they're even much earlier references, and they're grown by several groups. Some of the other groups are here in the audience who also grow that. It's a quite common system. I don't know how well you see it. So you have this triangle of MoSe2 surrounded by a triangle of WSe2. You get also more exotic, I don't know, triangular flakes or almost snowflake-like things. And our question was, where these two materials meet, how good is a covalent bond? Can I really just use this as some sort of exciton highway, or is this just a line full of defects, which is also good, then we would do other things with it. But the question was, how good is the quality of this junction and how broad it is? So here, Ute Kaiser's group in Ulm did some atomic resolution electron microscopy. And I mean, you really have to fit it and be an expert to see a junction here. I mean, in the beginning, they thought they take the sample, they do a very rough scan, they see a huge defect line coming up, and they say, ah, that's a junction. But it isn't. It's much nicer. So they had to do a fairly complex analysis to find the junction, and then they, according to their measurements, give us for this particular sample a junction really of 2 to 3 nanometers. Then we first measured the optical properties far away from the junction to see if it compares to this, very well-known and studied compounds, and we were pretty happy with what we saw in both reflectivity and absorption. And some sort of a trivial questions I had was, when we lift it off, do we break the two materials apart? We do not. We can encapsulate them, no problem, as you will also see on our poster presentation later. Okay, so the very first rough scan we did was to put our excitation spot here and then go across this junction with the motors that I'm not supposed to mention now anymore. And we have, of course, a huge excitation spot compared to the junction widths. So you have to do some deconvolution to find the junction here, for which we mainly use then Raman spectroscopy for this particular flake. So then we asked the first questions for us. If this is now a very abstract way of drawing this monolayer with a lateral junction, we then excite it with a laser. We create these electron hole pairs, and then just like ink in a water, as Florian said yesterday, just by pure concentration gradient, it will spread in space. Yeah? So first we wanted to check, are the individual materials okay before we go to this junction region. So here are the results. You can see for MoSe2, WSe2 away from the junction region, certain extension. It's not at 4 Kelvin, it's not super far. Very roughly speaking, if you don't live for a long time, you cannot go very far. They recombine fairly quickly. As many experts here in the audience, you know that the story of excitons and WSe2 is extremely complex. You have short-lived and long-lived species, and they're all spectrally integrated in this particular image. I just want to point at one of the questions here arising for us. We have, the community has shown in years of research that this one here is a spin-bright ground state, whereas this one has a spin-dark ground state. So ever these two reservoirs of excitons would have to communicate, we have to think about how that will happen. So just a snapshot. These are the pretty pictures away from the junction, yes, which are fairly circular. Then as you go spot on the junction, you already see there are more interesting things happening now. You would expect this because the band gap of WSe2 and also its excitonic transition is higher than MoSe2. So if I excite excitons in this part and they have some form of mobility, they would be able to go to the other side. What I just did with my hands, I tried to motivate in this PowerPoint drawing. So what's happening if the exciton diffusion is actually reaching the other side? So how do we access this information? We put our laser spot far away from the junction, somewhere here. We get a spectrum which corresponds to the two transitions we know from WSe2. This is now room temperature data. We then excite still in WSe2. We have in our experiment a much bigger detection spot than excitation. So we can excite in WSe2, and it is possible that we get already an MoSe2 signal. Yes? What that means for us is, as we are sure our laser does not reach the other material, the excitons must have converted from being in WSe2, MoSe2, and I detect the emission. And then, of course, once this blue excitation spot is entirely here, I get only MoSe2. So we tried to do a tick better. There have been some developments here also at AtoCube at the tip-enhanced experiments. So now instead of 500 nanometer, we try to go for something like 40. So this is done with a silver tip, which then, if you calculate the electric field we generate in a radius of about 40 nanometer, we are particularly have high electric field, and we still collect over a very broad area. So here, Hassan and Jean-Marie have really done some incredibly systematic work on many, many junctions. So what you see here is an average of that. So here we position our excitation. We then slowly move across and see what kind of material emission we detect. And you can see the MoSe2 emission starts already while the tip is still on this side of the junction. Okay? This is a fully encapsulated sample. Surprisingly for us, the one that didn't have HBN on top allowed the excitons to travel further. We do not have any super explanation for this. There has been a paper from Alexei Chernikov, Ermin Maric, and Misha Glazov, where they looked at scattering mechanisms. You can maybe imagine that in this slightly rougher sample, you have more of this kind of Auger scattering. With this, you do create excitons with incredibly high energy, and they then have the potential of going further. This is still an investigation, but that just means we have an impact of this 3 nanometer region more than a micrometer away from the junction. Yes, it's like you imagine a lake which is closed. You drip here, and you have some sort of wave. But if this lake has a waterfall on that side, the movement is going to go to that direction really far. Okay, so then we can call this some sort of a exciton diode. So as I'm moving towards the end, the next experiments which we try to understand at the moment, we have these really nice shapes, so we can bring these excitons in this low energy material closer to these focal points, where we then have, at the moment trying to analyze some of the reflection, as you want, of the population. And the other question we wanted to ask ourselves is, how does this transfer process actually happen? I mean, so far I just show luminescence on one side from one material, luminescence on the other side, and they are totally different exciton species. So how did they convert into each other? I cannot still fully answer this question, but we definitely have to pass through the interface. And at the interface, you already have to think about if your WSe2 excitons and your MoSe2 excitons are the only players in your rate equation, if you want. So you could also have a charge transfer exciton. Here, Emin Malic and Roberto Rosati try to calculate under what conditions this charge transfer excitons would be the lowest energy state. It can always exist, yes, but of course you would see it only in photoluminescence if it's the lowest. For this you need a certain condition of how wide this junction is. So we measured it for this one sample electron microscopy. For this one, yes, not for every sample we have in our PL setup, it's impossible. And for narrow junctions, this can indeed be the lowest transition. So at the moment, we try to further work on this. You can maybe see our poster for that. There are some predictions where this should appear. And I think more importantly, it will appear in the global balance of how strong is WSe2, how strong is MoSe2, and how many excitons go to this charge transfer complex. Okay, with this, I'm moving towards wrapping up all of this. So the corresponding poster here with details of the measurements you can see on Thursday, and the second poster, just to stay with the theme, we did optics on CRSBR, where we see some switching of Raman polarization modes. Why do I show these two different samples in the same talk? We are just building up labs, and the lateral heterostructure is so sharp. So this was our alignment tool for having the ultimate spatial resolution. And this, of course, compound, as you all know, is extremely anisotropic. So here we aligned all the polarizers and saw if things are behaving. And they didn't. We immediately found something that this material will give us extra. With this, I put on the conclusion slide with many open questions for us for these players, which we then, of course, then would try to integrate into heterostructures, which will then have homo and heterobilayer in the same sandwich. With this, I thank you all for your attention.
Talk. So I would have many questions myself, but still we have time for one very short question from the audience. So is there anyone interested? Okay.
Very interesting talk. So is there something to do with the bright exciton of MoSe2 or WSe2 at 4K that playing a bigger role?
So most of the far diffusion experiments we did at room temperature, just to avoid any localization. So can you focus?
Yeah. For MoSe2, you get bright exciton at 4K.
Yeah.
For WSe2, the PL peak quinches.
Yeah.
Right? So is it playing a bigger role in the 4K when you see that differential?
We have not done a temperature dependence of the efficiency of the transfer process. That would be interesting, but we have not done this. Yes. Okay. So it was our privilege for these samples to work at room temperature because they are fairly mobile, And as you know, the effective radiative lifetime is a bit longer at room temperature, so they could go quite far. That was on purpose, not only because we didn't have a cryostat first.
Thank you.